methodology regarding the grading. I'm done part of it. I'm not done all of it. That's why I didn't bring it. If for whatever reason you need to know as soon as possible what your grade is, please do let me know, and then I'll just do yours first. But as of now, I don't have major patterns. I think it is grading. I'm grading it out of 61 points. I have some people, at least one at 55 out of 61, and then I also have one at 10 out of 61. So that's the usual big range. So I don't know, but I haven't done enough to get a good pattern. One thing that I'm definitely, unless things go crazy, I would complete the grading and at least let you know the marks by by posting ID before next class, and then bring them to the next class. So that's what my plan is. And then on the other one, on the extra credit assignment thing, I forgot to say the deadline, but essentially I didn't mean it to be done by today, although apparently some people actually did it by today. So it's an extra credit thing. So if you think you need extra points, you can do that. I think it's basically, it's probably useful to just get it done by by the end of Thanksgiving break. But I'm not really, there's no actual deadline. If you do it before the end of the course, you can still come and tell me that you did it. Okay, I will probably follow it until end of next week. Okay, so that, and after that, if you post, let me know that you posted, because I cannot keep refreshing it every day. Okay, I'll also send it to, I think I'll ask Will Cushing to answer. I think some people actually had interesting questions already. So I'll give the link to Will Cushing, so he might very well answer some of those if you are interested in them. Okay, so that's regarding the extra credit thing. Okay, any questions before I start? Okay, so at the end of last class, actually, I said that a name is kind of important enough that I want to repeat it here. We talked about the fact that Markov chain Monte Carlo is the approach we were looking at. It's basically a Gibbs sampling approach. We looked at Gibbs sampling, which is a special case of Markov chain Monte Carlo. And there, in essence, first of all, I want you to understand a couple of points, because one is for this little network, you could see the entire Markov chain in front of you. You normally never see the Markov chain in front of you. You just simulate it, okay? And you basically, so a big question when you're simulating the Markov chain, and simulating Markov chain means essentially, if you are in a particular state, then you pick a node which is not one of the evidence nodes and resample it given its Markov blanket. And then you'll get a next state. And then you keep going around like this. Now the question, of course, is, so it's like somehow you start from scratch, and then you need to do some sampling, some sampling until you think you have reached the steady state of the Markov chain. Okay, this idea is basically called the mixing time of the Markov chain. So these things happen, right? So for example, if you're just putting on the, you're supposed to take, let's say, 5 minutes of shower. After the shower, water becomes hot, okay, warm. And so you let the shower go on for a while, and depending on how bad your piping is, it might be hot very fast or it might take longer time. So that's the mixing time. So once you think it has reached the steady state temperature, then you take your 5-minute shower. Okay, so this is the mixing time, and then after that, you then choose some K samples, and using those K samples to estimate all the probabilities. The question then is, how long does it take for the network to reach steady state? What is its mixing time? And one of the worst things that can happen, so in fact, if a Markov chain is not well behaved, one of the ways a Markov chain can be not well behaved is if in fact it's not ergodic. Okay, that means you don't reach every state from every other state with a finite probability. Okay, and I mentioned this last time, and I mentioned the fact that this has nothing to do with the underlying network being disconnected. Those are completely different ideas. So for example, if these 4 nodes were just completely disconnected, that doesn't make this network that doesn't make the Markov chain of this network non-ergodic. Because all that matters is, are you able to go from every state of the network? That means true, false, if it's all Boolean variables, every true, false assignment of variables to every other true, false assignment of variables with non-zero probability. And if the network is disconnected, all that means is all of them are independent. That still means you can reach TTT from FFF. The only time you cannot reach one assignment from another assignment is if some of the probabilities are zeros. If any probability is 0, that means some other probability is 1. Right? Okay? And if probabilities are zeros and ones, that is actually the special case of deterministic logic. In general, you would like to think that probabilistic reasoning is harder than deterministic reasoning. That's why in Intro to AI, for example, we look at logic first and then probabilistic logic next. So if there's parts of your world which have deterministic dependencies, in fact, Bayes networks allow deterministic dependencies. Okay, so if the parts of your network, let's see if there is any. So if you have a big network like this, for example, I could say, some variable here is actually a direct sum of these 2 variables, just, arithmetic sum of these 2, the top parents. Or it is the deterministic OR of these 2 parents. That's allowed, because Bayes networks are strict generalization of probabilistic logic. Generalization of propositional logic. Okay, and in those cases, you would think reasoning should be easier. And it is, except for sampling-based methods. Do you understand what I'm saying? So a problem can become easier in general, but not harder for a particular class of methods. And for sampling-based methods, if you have deterministic or close to deterministic dependencies in the network, then it's almost like it's kind of almost ironic that the problem becomes easier for anybody else because some of the things are deterministic, and yet the sampling approaches don't converge because the underlying network becomes non-ergodic. That means its Markov chain is disconnected. Okay? And as I'm saying this, I hope people understand that Markov chain being disconnected, if there was another exam, this would be a question I would ask. Okay, can you understand that Markov chain, a network can be disconnected while its Markov chain is not disconnected, and vice versa? Yes?
Should it be possible to remove a node with a 1 for the probability and simply reconnect because of the...
Those kinds of things are possible. Those kinds of things are possible. But part of the reason you might wind up having those additional nodes, might be because they play a role in their relation with other nodes. Okay. So in general, whether or not you have deterministic dependencies, you can always remove nodes from network. Adding nodes is opposite of removing nodes, and we said we wanted to add nodes to make the distributions more compact, remember? Okay, yes?
Now, when you say sampling approaches, do you mean all sampling approaches? Because it seems like if we just did a straight Monte Carlo instead of doing the Markov chain.
Markov chain in particular, because most of the specific one that, in fact, most of the people actually use Markov chain Monte Carlo as the sampling approaches. Those are like the state-of-the-art approaches right now. The rejection sampling stuff that I mentioned is actually used in particle filters, but that's about it. So in the Intro to AI, we talk about, normally we teach you rejection sampling and sampling from the rejection sampling and the likelihood weighting based sampling. But the Markov chain Monte Carlo is actually much more effective, and that doesn't work very well if you have deterministic dependencies. Again, this is sort of the, people would say this and assume that you would understand that, if you have deterministic dependencies, Markov chain Monte Carlo approaches won't work well. And that's because that's where the chain becomes non-ergodic. Okay. Now, of course, you can make a non-ergodic chain into an ergodic chain by taking the deterministic dependencies and make them slightly fuzzy. That means slightly non-deterministic, slightly stochastic. So instead of 1 and 0, you can say 0.9999 and 0.00001. That does make the network ergodic, but the mixing time is not going to suddenly become very small. So instead of having mixing time of infinity, which is what happens if you have different components of the Markov chain, the mixing time will still be quite high. Okay, what that means is, of course, nobody quite knows when they are doing these MCMC approaches, how far should you let the network kind of stabilize before you start taking samples. Did I mention my far side optimist drinking water in the desert cartoon? So this is very important. I mean, so there's this is the definition of optimist, I think. So these two guys are walking in some Sahara desert or something, and they're completely thirsty, and then there is a little tap suddenly in the middle of the desert. So the first guy runs, opens the tap, and starts drinking the water. And the second guy says, no, don't do it. Let the water flow for a long time, and then it will become cold. Then you can drink the cold water. Okay, now, I don't know why you people are not finding it funny at all, but you have a tap in the middle of the desert. You have no clue if there is going to be more than 2 drops of water. And you want to throw away the first 5 buckets of water just on the off chance that there will be cold water later on. Okay, to me, I don't know, that's like the definition of optimism. Okay, misplaced optimism. But anyway, so in essence, the same thing here. So you are about to say, somebody is waiting for the results from my network. Then, so your friend says, okay, I've done enough. It's now stabilized. I'm just going to take the numbers. Now you say, let it stabilize a little bit more, and then we take the numbers. It'll be even better. But then you might lose customers because they have left. Okay, but this is again, it's a it's a very interesting mathematical point about Markov chains and how to compute their mixing times and what do they depend on, and they do depend on how small the probabilities are. Yes?
Is there any sort of insight in how we select which of the variables we're going to try flipping?
Not so much. Not so much. I mean, obviously you don't flip the ones that are basically in the evidence. Okay? But everything else is there. Yeah. But again, there's like books. I mean, for every topic here, again, there are books. I mean, there are big books written on, Gibbs sampling. Even as I'm saying it, I think it's not so much means I am not completely aware of them. But if you search, I'm pretty sure there are some neat ideas. Okay. Yeah.
Does anyone does any work on maybe estimating the mixing time during network?
There are. I mean, again, there's a lot of work on, so you can study Markov chains directly from just a mathematical standpoint of view, okay? And then it's very big, estimating mixing times is like the biggest thing, okay? The problem, of course, is these are humongously large Markov chains, and, the connection between the theory, I mean, the theory might give you some bounds saying, mixing time will be below this much, and those could be very, very pessimistic bounds. So you can say that, I can say for this kind of a network, it will certainly mix under 2 years. The question is, are you going to wait for 2 years? Mathematically, it's correct. Okay, so under 2 years it will. Okay, yeah.
It seems to me like it might be best to just apply a windowing approach, where you basically have a window of k samples, and you just let that keep running as long as possible. And because you're doing this windowing, then you're getting, the k samples are getting better and better and better the longer you run them.
That's fine. That is fine. I mean, again, you can do this anytime oriented thing. That's obviously a reasonable thing, but sometimes you may actually have to take a decision based on your approach. And the question then is, when you do take a decision, it doesn't, if the underlying world, not the network, but the real world, if it's not ergodic, after you take the decision, you don't get to say sorry. Okay. By the way, my heart went out for this one student who said they didn't remember what ergodic meant in the exam. Okay. I realized that, for a lot of us, English is a foreign language, and in fact, you could be the smartest person who just doesn't happen to know what it means to say ergodic. I wish they asked me during the exam, but but you should know these words. I mean, I can't give you basically because everybody uses them. Anyway, so that's one thing that I mentioned on the email. Hopefully, some of you already read it, but I just thought it's important enough to bring it up. So now I'm going to actually today just talk about learning the Bayes networks, because that's also. By the way, all of what I've done is if you don't know this, it's very important anyway. If a couple of you have done 471, it's kind of repeat, but 471 with me, it's kind of repeat. I don't know others. So even though you can think of this as setting up the stage for LDA, it's also just important stuff by itself. You should understand how to do this. Okay, so how do we learn Bayes networks? As I said last class, we could assume that essentially somebody gives an entire network. So the other idea is, can we just learn the network from the sample, from the data? Okay. Now, so basically, if I have data like this, burglary true, earthquake true, alarm was false, John calling true, Mary calling false, blah blah blah. These are all the samples that I got. So I actually went around with. Remember last time I was saying, instead of going around with Perl, I can look at the network. But if I don't have the network, I just go around with Perl. And then understand what happens in his life and write a little network. And once I write this network, I don't need to start Perl anymore. I can just basically, everything about his life, is in this particular network. In this particular part of his life is in this network. So the question is, I got these examples essentially, hopefully by following him around. Okay, and then can I somehow from these examples figure out this is the network? Okay, this is the probabilistic distribution that would essentially generate this data. Okay, one way of thinking about this, is notice this is a distribution. Okay, so if you can generate samples from this distribution, right? Because there are many ways of generating samples from these distributions. If you don't have any evidence, this is basically empty network. I'm getting full samples. So I would start, burglary, earthquake, alarm, John calls, Mary calls. I'll just make samples, one sample at a time. And then I have a whole bunch of samples. I'm basically trying to see if I were to generate samples from this, they would look like these samples. Their distribution would look like these samples distribution. Okay, that's what we're thinking of. Okay, so yet another way is to say this thing actually specifically, succinctly defines a particular probabilistic distribution. These samples define an empirical distribution. Now you want to make sure that the distance between these is reduced. Okay, you can actually talk about distances between probabilistic distributions. We won't go into too much detail today, but there are these ideas called KL divergence. And you can actually think of, picking a network whose corresponding distribution will have the lowest KL divergence distance with respect to the empirical distribution. So that's what you're sort of thinking of doing. Okay, how do I do this? And this is where we basically will go in a slightly unintuitive direction. So first we'll start talking about something called, and I like this here. First we'll talk about Bayes learning. And we'll actually see that Bayes learning is not learning at all, it's just inference. Okay, in Bayesian reasoning, there is no difference between learning and inference. Once we understand that, we then say, well, it's too hard. And then we make it into two simpler cases. One is called MAP, MLE, and MAP learning. Actually, in fact, MAP and MLE. I'm sort of giving you sort of the approach that I'm going to use. We'll go into the details in a minute. Okay, MAP and MLE. MLE is very easy. Okay, and it turns out that, in fact, remember I kept talking about this whole deal about frequentist versus Bayesian statistics. The big difference is, the big point of contact is this. If you learn using maximum likelihood estimates, or MLE, that would be sort of essentially functionally equivalent to what frequentist statistics does when it's learning from samples. Okay, we'll do that, and then having gone there, then we will look at how to do MLE for Bayes networks. And then we'll notice that there is a simple case where you are given network topology plus complete samples. Complete samples essentially means that these are the samples, right? Now notice that these samples are observed by, by stocking Perl. I figured out the values for these in each of the samples. Now if your network is only made of those, that means if your network is only made of B, E, T, A, J, and M, which is the case here, then you have complete samples. But sometimes you actually think that part of the important issues here are things like the mental state of John, the mental state of Mary, for example. Okay, now those you did not actually get to observe. You think those hidden nodes, if you throw it into the distribution, it will be easier, it will be more compact. Okay, if you are doing that, then the samples you have will not tell you the values of those hidden variables. Okay, that can happen a lot. And so if you have given network topology plus complete sample, it's the simplest scenario. Next comes incomplete data. Next comes unknown topology. And next comes both. Okay, what's interesting is this is fine. This actually is the simplest kind of learning. We'll notice that when you are given network topology and complete samples, for Bayes networks at least, learning essentially involves taking ratios over the number of samples where certain thing holds divided by the number of samples where certain other thing holds. So it's just basically learning means taking ratios. Okay, and what is interesting is why does that make sense? And we'll actually realize that when you write the expression for maximum likelihood, when you write the expression for likelihood and maximize it using your calculus ideas of taking derivatives and equating them to 0, then you will get this answer, that the answer is taking the counts, the ratios of the counts. Okay, and that's the best case scenario. So Bayes network learning for the known topology and complete sample is like the easiest thing you can ever do. And then for incomplete data is where this expectation maximization idea I mentioned, we'll mention again today, where you kind of guess values for the missing variables, and then using that you can basically do the learning, and using the learned probabilities you can re-guess the values for the missing variables, and keep doing this until you reach you reach a stable point. Okay, that's the EM, incomplete data is EM, and that becomes harder. Okay, and then the other thing is unknown topology. That means I didn't give you topology at all. So if I were to give you just this, the most general learning is I just give you these samples. I don't even tell you that these are the only variables of relevance. There may be more variables whose values I don't even know. So I just have to make them up and put them into my network. That's the most general case. And I certainly don't know the topology of this network. Just a second. So what I would do is, the simplest case is I'll assume it's complete data and known topology. Next I'll assume known topology but incomplete data. Next I'll assume complete data but not known topology. And then finally I will be forced to take the most general scenario, which is incomplete data and unknown topology. Okay, and what happens while we are doing all this is that we will start, so you give up on Bayes learning in the very beginning, saying it seems like it's a great idea, but it seems like you can't do it. And then you do the easy cases. The easy ideas work fine here, but by the time you come here, you'll start realizing that Bayes learning actually works well. So you need to bite the bullet and support Bayes learning. Okay, the reason this is all interesting is because LDA actually sort of can be seen in terms of Bayes learning, with known topology but incomplete data. Okay, there was a reason. Yes.
So if there is incomplete data and we don't know the topology, so you say that we need to figure out the new variables and their probability. So if we just make the network according to the variables that are given, I think that it will adjust it automatically even without the other variables.
I don't know what you mean.
So we don't know some variables.
Mm-hmm.
Okay, so if we don't even include the variable when we are actually doing the learning thing from the samples, I think the network will automatically adjust itself without even those.
Just keep that in mind, keep that thought in the back of your head. We'll actually see that, and there are some interesting issues there. Okay. Any other questions? Okay, fine. So this one I'm going to go fairly fast, but you should be able to look at it in the textbook too. Here is a very simple scenario of Bayesian learning. Okay, no Bayes networks yet. Okay, so I'm thinking of very simple sort of hypothesis. I essentially have candies, and I put them in 5 different kinds of bags. Okay, so basically I have 5 different kinds of bags. Bag 1 is the hypothesis 1, which is there are 10%. There are 10%. So this bag 1 of type H1, which is this type, has 100% cherry candies. Okay. Bag 2 is this type. It has 75% cherry candies, 25% lime candies. Bag 3, 50-50. Bag 4, 25-75. Bag 5, 100%. Okay. So, furthermore, you've been told up front that this is the prior distribution of the bags. Pay attention to this word prior. And frequentists hate this. Okay, frequentists think that thou shalt not make any assumptions about the data other than the data. Okay, and so in fact, to the extent you want to understand the religious wars between Bayesians and frequentists, this is the word. Okay, so Bayesians assume there's a prior distribution. Now you might say, well, what's the big deal? If you don't know anything, just assume everything is equally likely. But that's still assuming something. It turns out. Okay. So, but for you guys, it's fine. It looks like, maybe the manufacturer makes, 10% of all cherry bags and 10% of all lime bags, 20% each of 75% cherry, 25% lime bags, and 40% of 50-50 bags. They may have done some major, consumer research and found this is the kind of bags that seem to sell well. So now, this is the scenario. So then, I have picked a bag. It turns out in this particular version of the problem, the bags all come in, brown paper packaging. It's like contraband. You don't want to tell what's inside. Okay. And so, this is sort of like M&Ms, right? I think recently there was this thing in M&Ms where if you get all brown M&Ms, then you can be a millionaire. And if you wrote, this is the all brown one, I'm pretty sure you can be all a millionaire by now. So you are picking candies from this this little bag, brown paper bag, and you're getting, let's say, red. It's a cherry, lime. Okay, as this is going on, I want you to do 2 things. One, actually the most important thing I really want you to do is, what's your prediction as to what would be your next candy? So you close your eyes, you basically are closing your eyes because you don't have any idea what's inside. You put your hand in, pick a candy, open it, and say, oh, this is cherry. Another one, lime. Another one, cherry, and so on. Okay? And now you picked about 5 of them. Now my question is, what do you think is going to be the flavor of the 6th candy? So if you picked n of them, I want to ask you, what is your prediction as to the n plus 1th candy? Right? This is essentially, basically the point of prediction. Now, you could go directly to that prediction, but you could also actually ask yourself, what do you, the point is, of course, while you are interested in predicting, you can also see that here, on the way to prediction, you can ask yourself, what's my feeling as to which kind of a bag I'm stuck with? Am I stuck with all cherry bag, or all lime bag, etc.? So that's your hypothesis. Picking the hypothesis, the most likely hypothesis, and then predicting based on that hypothesis. Now, what's interesting is general learning scenarios, things like the maximum likely code estimation learning scenarios, you would pick first the most likely hypothesis. And then you say, okay, so based on my 15 candies I picked, I'm pretty sure that I am stuck with a 50% lime, 50% cherry bag. Now, having decided that, my belief as to the next candy being cherry is 0.5. Next candy being lime is 0.5. This is how we would do. And so the part of picking the hypothesis is called learning, and part of prediction is using the hypothesis to infer. This is the normal way of thinking of learning. Now, from a Bayesian perspective, however, I would say a different idea, which is originally you have priors on the hypothesis. When you see the data, as you see each of the data points, you can compute posterior on the hypothesis. Okay? Now, once I know the posterior distribution of the hypothesis, I can compute the most likely distribution of the next candy. In doing this, what Bayesians avoid doing is they never jump to any conclusion. Bayesian learning, to me, is the most least committed form of learning. We will not figure out, we won't say the world works this way. You'll say the world works this way with 0.7 probability, this other way with 0.2 probability, this other way with 0.005 probability, this other way with 0.007 probability. And if the world works this way, then tomorrow there would be, the following event with this much probability. If it works this way, this event will occur with a different probability. If it works this way, it will occur with a different probability. Now I take a weighted summation to predict the probability of this event occurring tomorrow. So you never jump to conclusions. Now, what's interesting is learning is jumping to conclusions for most of you, because you sort of inductively pick a hypothesis and stick with it. And what Bayesian learning says is you don't actually have to do it. So the word learning is a misnomer for Bayesian learning, because you never actually pick anybody. You see what I'm saying? Okay, so in this example, continuing, so there are two issues in this case. One is what kind of bag am I picking the candies from, and what flavor will the next candy be. And in some sense, if you are picking one bag first as your most likely hypothesis, and using that hypothesis to figure out what the next candy is, that's the general learning versus inference difference. Bayesians will say what you're doing here is you're getting the posterior on the bags based on the data. And using the posterior distribution, then you are predicting the posterior the distribution of the next candy's flavor. Okay? So now what are we doing here again? So you suppose you have h is the hypothesis variable, which can take values h1 to hn. Okay? And there is a prior over this hypothesis, p of h. So in our example, these are the different kinds of candy bags. This is the probability that there are 10% of them are all cherry, 10% of them are all lime, etc. That's a p of h. Okay? And then I have data, and this hypothesis actually causes the data. So in fact, I can think of this as a little Bayes network. Okay? So this hypothesis causes d1, d2, etc., dn. Now notice that the way I wrote this Bayes network, d1 is independent of d2 given h. Right? Because that's the Bayes network semantics. That's what is meant essentially. And furthermore, if I also say all of them, have, now for d1 requires a CPT, d2 requires a CPT, dn requires a CPT. In general, they can all be different. But suppose I decided to give them all the same exact CPT. That means the hypothesis, identically, under the hypothesis, each of these data points are identically distributed. The same CPT. Okay? And they are independent. They are independent of each other given the hypothesis. This is what is called IID. Okay? IID data. Okay? They are independent and they are identically distributed. So in fact, here's one little thing I'll throw in. If in fact it is the case that H causes D1, D2, D3, etc. And then this CPT is the same as this CPT is the same as this CPT. Why am I writing this whole thing in this longhand? What I would like to write is some kind of a shorthand and say, here is the hypothesis. Hypothesis causes D. And I put it in a plate. Okay, and in fact, this thing goes inside. And this is called the plate representation. Okay, and then I'll just give the CPT just for this. And if I have 15 data points, then I essentially put 15 of them one next to each other. That's unrolling the network. Again, in LDA, you use these plates. You know, if you started looking at it, you see these plates. That's because essentially you are writing, networks of the form where hypothesis is causing the data, but it's causing the data with the same distribution. And furthermore, this structure essentially means the data are independent of each other given the hypothesis. Okay, so having said that, now of course in this particular case, what I need is given the data so far, now I can compute the posterior probability distribution on the hypothesis using the Bayes rule. Because I'll assume that, suppose in that example, if I am with a 75% cherry and 25% lime hypothesis. That's my hypothesis. Okay, what is the probability that I will get a cherry given this hypothesis? 7.75. Right? So you know that hypothesis provide sample given the hypothesis probabilities. That's what hypothesis provide. Okay, so hypothesis provides PD given H. D being the data given H, which is the hypothesis. What you need is PH given D, which is the posterior probability distribution over the hypothesis given the data. Okay, and that basically you use Bayes rule. Okay, PH given D is PD given H times P of H divided by P of D. Right? That's the Bayes rule, right? PH given D is P D given H times P of H by P of D. Now, we do the usual trick and say, I don't necessarily know the probability of the data. Okay, however, I don't need to. I can just say alpha times. And then compute the probability for H1 given D, H2 given T, H3 given T, which will all be in terms of this alpha times 0.7, alpha times 0.3, alpha times 0.6, and so on. And then from that, since all of them should add up to 1, you can compute alpha. That's the usual trick. Okay, that's why you write PHI given D is alpha times PD given HI times PHI. Right? Nothing new. It's just application of Bayes rule. Now the interesting thing, of course, is P of HI is the prior distribution. So that's where the prior distribution was being used. Okay. Now, if I have figured this, distribution out, PH given D, after seeing 15 samples, I have figured out PH given D. Then what I need to compute, for my prediction, I need to compute what's the probability of the next sample given all the data I have seen till now. Which can be seen as essentially probability of the next sample given all the data and hypothesis times hypothesis given data. Okay, and then you sum over all the hypotheses. So this is what I was saying. If the world was working in method 1 with 0.7 probability, method 2 with 0.3 probability, and if world is working in method 1, tomorrow there would be this event with 0.2 probability, and if it's working by method 2, there will be this event with 0.7 probability. Then you can compute the expected probability of this event occurring tomorrow. You see what I'm saying? So that's what this thing is saying. Now the only thing, of course, is Px given D and HI is, now notice that the data, the next data, here's the deal. This is where everything is important. So if I have seen, I have a hypothesis. I've seen data 1, I've seen data 2, and I'm trying to figure out what will be data 3. What will be data 3? Right? So now that is data 3 given hypothesis and D1 and D2. But data 3 given H and D1 and D2 is the same as data 3 given just H. Because D3 is independent of D1 and D2 given H. Bayes network again. Right? Okay? So, that's all I wrote here. Now if I take this is learning. I mean, you can call this learning, you can call it whatever you want. You are able to predict the next guy, and you're also able to keep track of the posterior distribution of the hypothesis as the data is being seen. So, okay, so here's a nice picture which kind of illustrates what happens as you keep seeing samples, okay? And the samples are basically, in this particular case, imagine that the samples are all line, just line. Okay, now, and the way to look at this is, this axis is actually, this picture is telling you the prior distribution over hypothesis. At 0 samples, the distribution for the hypothesis is these numbers. Right? Okay? And so there are, so this is color coded. So H1, H2, H3, H4, H5 are those colors. Okay. And so there are 2 numbers. There's basically, so this, now this is for 0 samples. And by the time you get to one sample, and that's a lime, you notice that H1 given D goes down to 0. Because H1 is supposed to be the hypothesis that the bag is all cherries. If it's all cherries, then you must not see even a single line. So the moment you see a single line, the probability that the bag is all cherries goes 0. So that you can see. And other guys change in between slowly. And what's happening in this case is, so at any point of time, if you want to find out what's the posterior, that is the posterior distribution. It's a beautiful picture, by the way, because normally you can't write this kind of a picture for the priors, because the priors are, the distribution on the hypothesis is changing as the data is being seen. And you need a nice picture for how the distribution is changing. And here you can actually see how the distribution is changing just by looking at the y-axis. That's the nice thing about this example. Okay, now of course, as you can see, after a while, essentially, the hypothesis in the posterior becomes more and more peaked. That means it have a strong peak at all line. Because you're getting line, right? So the all line box should become more and more likely. So by the time you came to 2, all lines is more, is actually somewhat less likely than 75% lime and 25% cherry. But by the time you come here, it already became the most likely. But these guys still have non-zero probabilities. By the time you came here, everybody else is close to 0, except those 2 guys. And this one is 75% lime, 25% cherry, and that one is 100% cherry. Okay? So this you can draw yourself by just using those numbers and using Bayes network. And this is just showing you what is happening. So in general, during learning, in Bayesian learning, as the data comes in, you are updating the posterior on the hypothesis. And based on the posterior on the hypothesis, then given any of these distributions, I can then compute what is your prediction about what is going to be the next candidate. Obviously, here there is some kind of a question. By the time you come here, there is very little question. Right? It's going to be line. Yes?
So are we assuming that by taking a sample that doesn't change the probability of the distribution in the bag? So like for example...
Yeah.
Okay.
Yeah, so this is, again, I know that you are thinking of the earn models. learned models basically are talking about what is the probability if there are 15 red balls and 3 green balls, and what's the probability that the first ball would be green, and then what would be the probability that the second ball would be green, will be smaller, the third ball green being different. But right now you are not asking the prior probabilities, you are asking conditional probabilities. Conditional on the bag. Okay? So in this bag, when you pick and you assume, to make our life simple, we assume that each of these bags have infinite number of candies with those fractions. Okay? Now, if in fact they don't have infinite number of candies, then what goes wrong?
Then we can easily figure out which bag it is, and then we can put it.
Right, which one?
No. So in this picture, what changes?
Our predictions would then depend
Not
on
just,
the
no, now I'm asking for something slightly different, which is, will candies be independent of each other, given the hypothesis?
There will be
no. That's what it is. Again, please, this sort of mental exercise is important. People can do Bayes network learning. There are toolboxes for doing Bayes network learning. You can just switch it on and you'll do it. Okay. The real question is, do you understand what it is doing? That's all. Okay. And understanding that making sure that you understand is putting these kind of questions and seeing if you can make sense of what happens to your model. So this model is where I sort of said, so this model is where I'm sort of saying that what you are worried about won't happen. Because if it happens, that means you're dependent on not just the hypothesis, but the number of candies that have been picked. That means you are dependent on the data. Yeah.
So in general, in learning, we have a training phase and we have a verification phase. So what will be the verification for Bayesian learning?
The reason, this is the second time I'm doing this, right? The reason for you, he was also in 472. The reason Bayes learning is interesting is because it plays with your intuitions about learning. You think learning involves picking a hypothesis first and then using that hypothesis forever. Bayes learning, there is no such difference between picking and predicting.
So it's kind of always correct.
It's always connected. It's basically, currently, if you stop it, this is its posterior. Then this is the posterior, this is the posterior, and so on. Now, you can see Bayes network, think of the following scenario. When do you think Bayes learning would be more useful versus less useful in terms of picture like this? If the hypothesis prior, suppose if the prior on the hypothesis or the posterior on the hypothesis for a few steps in time, it all turns out to be sort of uniform or sort of basically it's not a sharply peaked distribution, then Bayes learning is more useful than non-Bayes learning. Because you have, if it is sharply peaked, then Bayes learning is not useful. Because by the time you come here, this guy is so much higher than everybody else. If you just pick this, the weighted prediction wouldn't have been any different. Whereas somewhere here, you actually are not sure about your hypothesis. So it's like the following thing. Suppose a patient comes, you made test 1 and test 2 and test 3. In the beginning when the patient comes, patient can have diseases D1 to D1000. And if you give them all the medicines, the insurance won't like it. Okay, now you do 2 tests, test 1 and test 2. At this point, you think the patient has either disease D1 with probability 0.51 or disease D2 with probability 0.49. Insurance will say pick one. So you just pick 0.51 and then only treat that disease D1. But the poor patient may actually be having disease D2 because that's a pretty high probability event, 0.49. Do you see what I'm saying? By picking on, by being forced to pick a single hypothesis, you could be wrong. Okay? Whereas Bayes prediction can never be wrong. In the sense, in fact, one of the things that, in statistical learning, the line in the sand is Bayes optimal. You will say if a learning algorithm is equivalent to Bayes learning in terms of its prediction power, then it's Bayes optimal. And if you can reach that without having to do all that Bayes learning does, which is what all it does is keeping track of this entire hypothesis space posterior probability. Okay, if you can do it without doing this entire posterior probability, then you get some points because you're doing the optimal thing or close to optimal thing without paying the price. So on one hand, Bayes learning is conceptually doesn't require you to think of there being a learning. It's just all the same. It's just inference. But computationally, it's very painful. Because computationally, you are keeping track of the posterior on the hypothesis. It's always easier to pick one value, one hypothesis. That's what MLE does. Okay, that's where we're going to go now. Okay, so if you have these kinds of predictions and these kind of posteriors, then at each point, if I were to ask you what's going to be your prediction that the next candy is going to be a lime, then this is how the probability of the prediction is. So here you will say, I am 0.65 certain that the next one will be lime. Here you're saying I'm 0.7 certain. And by the time here I'm like 1.0 certain that it will be a lime. I mean, you'll never say 1.0, you'll say 0.9999999 certain that I'm. Now this is another very interesting thing about Bayesian learning, that you can provide a confidence in your prediction. You can provide a confidence in your prediction. Suppose for whatever reason that you just pick this as the hypothesis. And you will then forget what was the probability of the competing hypothesis corresponding to this, compared to this. So then according to this hypothesis, you will make the prediction and somebody says, how sure are you? So I don't know. What is the way you can be sure? If you did not compute the posterior distribution, you don't know. How likely is that you are right? You understand that? Now, you might say, well, maybe you know that this is 0.5, so you're 50% right. You could actually be more than 50% right, because maybe if all these other hypotheses will also give the same prediction, then the prediction probability is higher. It is the ability to keep track of the posterior that allows you to give the confidence on the prediction. You see what I'm saying? Okay, so that's all the singing praises of Bayes network, of Bayesian learning, which is not learning, which is just inference. Okay, and then we will go and differentiate them. Let's see, wait a minute. I lost that slide. Yeah, this one. I don't know why you. So I don't really want to hang around with the posterior distribution. I want to pick a winner. Okay, I mean, it's like, imagine, this is a nice way of thinking about, and I won't go into that, but anyway, although I do like that like even this year, for example, Bayesian learning would allow both Romney and Obama to make decisions as we go forward. Right? Because, it's not, it's like Obama got like 5 more votes than, the other guy. And the same thing in 2000, the guy who won, got like 537 votes more than the guy who lost nationally. I mean, not nationally, actually, it's a different situation. But the point is, Bayesian learning won't pick a winner. And that's why its life is harder. Okay, normal learning picks a winner, so it could be the wrong winner. I mean, some of you, half the country thinks we picked the wrong winner, and half the country thinks we picked the right winner. But we are stuck with that winner. Because if only we had 2 rooms in White House, we didn't have to pick the winners. Anyway, so if you don't want to keep multiple winners, then what can you do? One idea is, remember that in doing the prediction, basically you are computing this. Let's see. Okay. When trying to predict the next sample, you are summing this expression. This expression gives a number for each of the hypotheses, if you have discrete hypotheses, by the way. Right? Now suppose, so there is one number, there will be, if there are 5 hypotheses, there will be 5 such numbers. And you are adding all of them to compute the probability that the next one would be like. If one of them dominates, one of these numbers dominates every other number by far, then adding a little doesn't change that much. So I can approximate this sum by its maximum component. Okay, which would be good if in fact the maximum is much bigger than everybody else. It'll be quite bad if it's not. Okay, but if I do this, that means I just pick one winner by essentially taking the particular hypothesis for which this element would be, this particular component would be highest value. Okay, and if I do that, then essentially I will get what's called the map approximation of Bayesian learning. Okay, where you are picking the hypothesis, a single hypothesis, not all, you're not hanging on to all the hypotheses, you're picking one single hypothesis such that it would give this component to be the highest value. Now it's hard to kind of make sense of that, so if this has the highest value, the log of this will also have the highest value because log is a monotonically increasing function. Okay, so if I take log of this, then this is log of p du hi plus log of p hi. So what I'm trying to do is pick the hypothesis which has, if you ignore the log part, which gives the highest log likelihood to the data. That means under that hypothesis, the observed data would have been most likely. If you have like two hypotheses, one hypothesis says there is 25% cherries and 75% lime. And the other hypothesis says there are 75% cherries, 25% limes. Notice that if I keep seeing lime, both these hypotheses could have predicted this data, except the data is much more likely if it is 75% lime, 25% cherry, than 25% cherry, 75% lime. I'm sorry, 25% lime and 75% cherry. Okay, so so that's what I'm saying. So I picked the hypothesis that will maximize the likelihood of the data. That's one part. The second part is I also add to that the hypothesis that is actually more likely. Okay? And then whichever is the hypothesis that winds up maximizing this sum, I'll pick that. And that essentially is maximal map learning. And here you are essentially saying if there is a crazy conspiracy theory that will explain the data with 100% accuracy, but the conspiracy theory's likelihood is 10 power minus 95. Thou shalt not assume that that's just a good learning, as good a learning as any. Do you understand that? Because I can make conspiracy theories which explain anything with 100% probability. But then, why am I not supposed to do it? Because the likelihood of that conspiracy theory, the prior likelihood that the conspiracy theory is actually true in the world you live in, is supposedly very low. Okay, and in general, this is where a bunch of terms such as Occam's razor, come. That means pick the simplest hypothesis that will explain the data. Where the word simple is highly loaded. Okay, simple means the one that has the higher prior. That's what it really means from the point of view of probability. Pick the hypothesis with the higher prior. Now this is where frequentists will say, how do you know that there is a higher prior? I mean, how do you know there is even a prior? And so frequentists obviously do not even like this. This is not Bayes learning, this is already one step below. I'm just picking one of the hypotheses. And they won't like that either. Yes, there's a question.
Yeah, I apologize if you already said this, but what base are you using for those logarithms?
It doesn't really matter. It's just log. I mean, it doesn't really matter, but I mean, I think people normally assume, natural logarithms, for like making life simple. But it's just any log is fine, right? But you assume, if I don't say anything, it's natural logarithms. Okay, so that you can say d by dx of log x is
1 by x.
Yes. Those of you remember that, you're in good shape for the next lecture. Those of you who don't, better remember it. Okay? Because you don't have to touch derivatives because you are computer scientists, supposedly. But you will have to now, pretty soon. Okay?
I think the base would be 2 because it says bits to encode data.
No, you could also think about, you can play this game any which way, okay? You can also think in terms of bits to encode data and provide that, but that's just a constant times the number. All logs are constant times each other, right? So, okay, so then the next one is, I'll say to heck with P of hi. Now when can I say to heck with P of hi? Notice that, what is this term, log of PD given hi? What is that term? That term is like this. Log of P, notice, I don't know if you notice, it's the D is in bold. Right? D given hi. That's nothing but log of D1 and D2 and D3, etc. and D1000 given hi. Right? Now, according to the picture that we had of the network, this would be equal to PD1 given hi times PD2 given hi times PD3 given hi, etc. Right? Now when you take logs, then that's like a little sum there itself. There's one little number for each data point. If you increase the amount of data, these little numbers can add up to a pretty big number. And they can overwhelm anything that P of hi is giving. Agreed? Do you see what I'm saying? So as the amount of training data increases, this is a very important point. As the amount of training data increases, your priors don't matter. Now this is true anyway, because even if you went with this, your prior would just get ramroded by what the data is telling you. But if you start by assuming that I will have lots of training data, then upfront itself I can assume that I just get rid of this. In which case I'll only need to basically find the hypothesis that maximizes just this number, log of PD given hi. So that's the log likelihood of the data. So pick the hypothesis that maximizes the log likelihood. That's the learning part. Okay, so there is basically MLE, which is further simplification of map. Map is actually a simplification of baseline. Okay, now when you are picking the maximum, now the one last missing point is, until now the only example you have seen is discrete hypothesis spaces, where you have H1, H2, H3, H4, H5. That's why you had sums. Normally, you have continuous hypothesis spaces. Now, where do you have a continuous hypothesis space? Let me go there. Okay, so I'm going to actually, this will be the last thing probably we'll get to do at depth today. Okay, so suppose I actually am trying, I've been given, this is a slightly different, slightly more nuanced candy example, where the manufacturer has basically picking the flavor of the candy, okay, and then putting it in a wrapper, and the wrapper is not always the correct wrapper. They have realized that they're not getting rid of cherries or something, okay, so they started sometimes putting cherries in the lime wrapper so that people will somehow put it in their mouth and then throw it away or something, okay, right? So there is certain amount of probabilistic dependence between so notice that if it is completely the case that every time there is a cherry you will put a lime jacket on it, then people will figure this out soon enough. It has to be probabilistic. It has to be this game theory stuff where you essentially have to put a probability so that people have to open it to figure out. Okay, so I'm getting essentially, then in my case I am looking at let's say I got n candies out. There are RC red wrapped cherry candies, RL RC red wrapped cherry candies. Then what are green? So GC green wrapped cherry candies. okay, and then RL, red wrapped lime candies, and GL, green wrapped lime candies. That's what I've gotten till now. Based on that, and I also know, basically, I've been told that the flavor depends, the wrapper depends on the flavor. That means the manufacturer first picks the wrapper, first picks the flavor, and with some probability picks the wrapper. Now, obviously, the flavor they are picking with some probability theta of it being cherry and 1 minus theta it being lime. And if it is cherry, with probability theta 1, you are giving it a red wrapper, and 1 minus theta 1, you are giving it a green wrapper. And for lime, with theta 2, you are giving it a red wrapper, and 1 minus theta 2, you are giving it a green wrapper. This is what I think is the network behind. Now, this is my hypothesis. This is actually a family of hypotheses. How many hypotheses are there? Infinite number of them. Because these are all real numbers. So every value of theta, theta 1, theta 2, this three-dimensional vector, every value of this three-dimensional vector, theta, theta 1, theta 2, is a network. What I'm trying to figure out is which would be the best network given the data I have seen till now. Okay? Bayesian learning would have tried to keep track of the posterior over this infinite number of hypotheses, which is why I won't talk about it now. But we will have to bite the bullet soon. Okay? Whereas maximum likelihood learning, all it needs to do is for this hypothesis H, compute the likelihood expression. Compute the likelihood expression. So what would be the likelihood expression? Here, so suppose I have the flavor is cherry and wrapper is green. Given my current hypothesis, notice that my hypothesis can be completely specified in terms of theta, theta 1, theta 2, because I've already decided on my topology. Topology is constant. So, what is the probability that flavor would be cherry and wrapper would be green given h theta, theta 1, theta 2? That would be probability given the topology of the network, probability of flavor being cherry given the hypothesis, times probability the wrapper being green given flavor being cherry and hypothesis. That's just Bayes network. Okay. Now for this, flavor given cherry is theta. I don't know what theta is, but it is theta. And wrapper being green given it is actually cherry candy is 1 minus theta 1. Do you see that? 1 minus theta 1. So for every GC, this one basically is the GC, right? It is, notice that I said there are total number of n candies, of which there are RC red wrapper cherry candies and GC green wrapper cherry candies and RL red wrapper lime candies, GL green wrapper lime candies. So RC plus GC plus RL plus GL equal to N. For every one of the RC data, for every one of these RC samples, I will get this product, theta times 1 minus theta 1. And remember that the total data probability has to be multiplied, right? Because they're all independent data. So I will get theta power RC plus 1 minus theta 1 power RC. Agreed? Okay? So theta power RC 1 minus theta 1 power. And so wait, that up to here. Okay, no, 1 minus theta 1 power GC. Yeah, you're right. Theta power GC plus 1 minus theta 1 power GC from the these guys. Okay, and from these guys, you will get theta power RC times theta 1 power RC. Right? And from these guys, I'll get theta, this is line, right? So 1 minus theta power RL and times 1 minus theta 2 power RL.
Shouldn't that be RC plus GC?
Which one?
Theta is the power.
No, but when I multiply all of them, you would actually add up those numbers. Okay, right? So if you do all of those, then essentially you'll get thetas, basically you'll get this expression. Just convince yourself that you'll get this expression. Where C is just the number of cherries, RC plus GC. And L is number of limes, RL plus GL. So it turns out this is the expression for likelihood of the data given the hypothesis H theta, theta 1, theta 2. I need to maximize it. I just maximize it, okay? Now, this is a function of what variables? It is a function of 3 variables, theta, theta 1, theta 2. So, one simple idea, basically from the calculus, and also this is a continuous function, because thetas are all continuous quantities. So, I can take the partial derivatives, equate them to 0. At least I'll get the critical point. Nobody told you that that is going to be the maximum. If you are into, if you're doing calculus 101, then if you just do this and stop and say it's maximum, they'll cut off points because you didn't do the second derivative test. But we won't do the second derivative test right now for now. But it turns out, so I can maximize this. To maximize this, first of all, one other idea is you can maximize the log of this, and that will be fine. Right? Because log of this entire quantity would be maximum exactly when this entire quantity is maximum. And if you do the log of that, then you get C log theta plus L log 1 minus theta plus RC log theta 1 plus GC log 1 minus theta 2. Okay? Now if I take the partial derivatives with respect to theta, theta 1, theta 2, equate them to 0, I'll get a bunch of equations. If I can solve those equations, I'll get the best values for theta, theta 1, theta 2. Now normally, before I go to the next slide, you have no clue as to whether each of the partial derivatives on theta, theta 1, theta 2, whether they would be independent equations, each of them on only one variable, or simultaneous equations, each of them in all 3 variables. Okay. Furthermore, you also don't know whether they will be linear equations or non-linear equations. If you are unlucky, they would be simultaneous non-linear equations. Do you see what I'm saying? And which is why there is a whole theory of mathematical optimization, where they will take, large multidimensional functions and try to find the minimum for this multidimensional, minimum or maximum for this function, using gradient descent techniques. So having set you up for huge disappointment, you should be really happy that what happens for you is that each of these, the partial derivatives are in exactly one variable. And furthermore, they are all linear equations. And furthermore, if you solve it, you say theta is C by C plus L, theta 1 is RC by RC plus GC, theta 2 is RL by RL plus GL. And this is like the most intuitive thing you would have done if you did not know anything about calculus. Right? But you had no clue whether it was right or not. Anybody can say something, but the question is, under what condition is it right? Okay, under the maximum likelihood estimation conditions, in fact, picking theta to be the number of cherries by number of cherries plus limes you have seen till now, and theta 1 to be the number of red wrapper cherries by number of red wrapper cherries plus green wrapper cherries you have seen till now, and theta 2 to be RL by RL plus GL, is in fact, probably, theoretically, the correct thing to do. Right? Now here's the interesting question. I said things can be very bad, and it did not become bad in your case. Will it always remain so? If I didn't have this network, but instead I have this network, will I still be able to be sure that essentially I will have parameters which are not entangled. That means each parameter will have its own equation. And they are all linear equations. Unentangled linear equations. That's like the best. If your linear algebra professor gave you solve for x and y and z, x equal to 2x plus 1, y equal to 2y plus 3, and z equals to 2z minus 4, say, yeah, this is great. Okay, but if they said solve for x, y, and z, x equal to x squared plus 1, you started being unhappy. If they said solve for x, y, and z, x equal to x squared plus root z plus y squared, and so on, then you are really unhappy. The most general case, the third case, is what happens. The most interesting thing that you want to be happy about is if you ever have Bayes networks and you have CPTs, basically tabular conditional probability tables, and you have complete data, which is what we've been looking at. You can always be sure that even if you went through the motions of writing the entire log likelihood and then maximizing it, you would actually essentially get the most obvious interpretation, which is ratio of the counts. So for example, if I have this network, and I have a bunch of data, and I want to compute what's the probability that John calls given alarm, that's nothing but I will set it to be the number of data items when both John called and alarm is true, divided by the number of data items where only alarm is true. This is what you would like to do. And I just gave you permission to do it. But you better remember how you got that permission. You got that permission by starting at the base learning, which is the right thing to do, deciding that's too painful, let's do map, and deciding further that if you have too much data, then map basically becomes MLE. And then, compute maximizing log likelihood, you will get just counts-based ratio. Now, when will this not happen? It won't happen even for complete data in Bayes networks if the CPTs, if the conditional distributions are not necessarily CPTs. Okay, basically the CPTs means you don't have a parameterized distribution. Okay, if you have, for example, the probability of A given B and E is some sort of a Poisson distribution, that can make your life unhappy. Because then you will be differentiating the Poisson distribution. Okay, whereas here it's all in terms of theta power L and theta power 1 minus L, and you are taking logs of them, and then it becomes nice. Okay, so if you have parametric distributions, this is no longer going to be true. It will also not be true for an entire class of graphical models, which I did not talk about at all in this class, called Markov networks, which is like, graphical models literature is one half Bayes networks, another half Markov networks. And if not half, less small. If you say half, you feel really bad that you're missing a whole half of the picture. But there is an entire class of models called Markov networks. For Markov networks, again, this is not going to be true. However, it will be the case that you will have essentially a bunch of nonlinear equations. And then what you will have to do, you have to do Newton-Raphson method. You guys remember Newton-Raphson method?
Yes.
Okay, so you need to find the zero of this guy. Remember, you're trying to find the zero of a differential, of the derivative. To find the zero of the differential, you start from some point, find the derivative there, essentially find this place, okay, and using that you can go towards zero. Okay, and in particular, the next xn will be xn minus f dash by f dash. But since we are actually playing with f dash, which is the derivative itself, then you get f dash by f double dash. This looks very nice as long as you stick to single variable calculus. F dash and f double dash are very similar in single variable calculus. In a multivariable calculus, what happens to f dash? It's a vector. What happens to f double dash? It's a matrix. It's called the Hessian matrix. Okay, and it turns out, while it is true that actually Newton-Raphson method for multidimensional case is the way you will like to find the zeros of this derivative, and then that's how you compute the optimal parameters. Actually, efficiently implementing Newton-Raphson method is too painful because you have to carry along these SCMs, which is double derivative matrices. So you do all sorts of approximations to that. That is mostly your mathematical optimization books. You do all sorts of things which are related, but not exactly Newton-Raphson. Okay, so the good thing is you ducked a bullet. You didn't have to know that really, because for Bayes networks, for CPTs and complete data, it just counts.